Is the light okay? Alright, so let's get started. So for this class, I'm going to talk about, or for this lecture, I'm going to talk about recurrent neural networks. So over the past weeks, we've looked at network architectures.
What? Just the lights?
Do you know how I can turn it off?
I think he just basically does like all of them except for like the second server, right? That includes like all of them but the second one. Something like that.
Okay. Thanks.
Okay.
Is it okay?
The one just to the right.
Yeah, so you keep that one off. Turn on the one. Yeah. Perfect. We did it.
Is that okay?
Perfect.
Alright. Okay. So as I said, our lecture for today is going to be on recurrent neural networks. And over the past weeks, we've looked at network architectures that's followed or had the flavor of the vanilla neural network. So for those type of networks we did look at, they receive a fixed size input, which could be an image or a vector, and then that's fed into a set of hidden layers. And we produce a single output. And that output could be a set of scores over categories or classes if we are working on a classification task. Okay. So now we may have different type of problems. We may have a machine learning task that may require our network to be able to handle different type of data and also produce different type of outputs. And RNNs give us that ability or that flexibility to handle different type of data respect to the size or the size or the length of the inputs, and also produce outputs of variable size or length. So before we dive deep into our lecture for today, I want us to look at the type of RNNs that we can have. So based on our task or our machine learning problem, any of these models or setup could be very beneficial. So for the one-to-one RNN, it takes a single input and then produces a single output. And one thing we have to note about the one-to-one RNN is that the current input depends on the previously observed input. So a classic application of the one-to-one RNN is a text generation task. So for the text generation task, what happens is that our previously predicted output is used as an input to predict the next word. Is that okay? All right. And for the one-to-one, for the one-to-many RNN, it takes a single input and then produces an output of variable length or size. And an example of a task where we could use the one-to-many is an image captioning task. So for an image captioning task, what happens is that we feed in a single input, and then the network produces captions. So we feed in several images, and then the network produces captions. And these captions could be of different words. And hence, we need our network to be able to produce output of variable sizes or length. And those are the captions. For the one-to-many RNN, what happens is that our network takes in inputs of variable size or length and then produces only a single output. And one typical application is sentiment classification. So for sentiment classification, we feed in our text or our sentence or the text we have, and our network predicts the sentiments over the text. It could be positive or a negative or sentiment. So in those setups or in this kind of machine learning problems, the one-to-many RNN can be used. Also, for the many-to-many RNN, what happens is that the network takes in inputs of variable size or length, and then produces also output of variable size or length. And one application also is the machine learning task. So, sorry, machine translation task. So here what happens is that we want to translate a sentence or a text from one language to the other. So say from English to say German. So we feed in our sentence or our text, and then our network translates that and gives us an output which is also of a variable length or size. So one thing we notice is that it's not always the case that when you translate from, say, one language to the other, the result you get will be of the same length or size. Some language just uses just 2 characters to represent a lot of things. So meaning that we have to be able to make our network model this kind of situation where we feed in inputs of variable size and then it produces output of what variable size. Okay, so now let's look at the last one, which is also a many-to-many. So for the last type, that's the many-to-many, one typical application is the video classification on frame level. So in this case, we feed in an input of variable size, and what we want to do is that for each and every element in our input, we want the network to make a decision or a prediction on that element. So we may feed in a video, and the video might have multiple frames, and we want the network to predict the action on that frame. So what is happening within that frame in the video. And in that case, we could use this type of setup for the many-to-many. Okay, let's move on. Let me move on to the next slide. I hope everyone is okay. Are you clear? All right. Okay, so before I move on, I'd like to acknowledge the source of this slide. So I took this class last semester, which was taught by Dr. Vivek Kumar. I think some of you know those of you who have taken the machine learning class. Yeah, is the one here. So this slide is from him, and I want to acknowledge it before I proceed. All right. So with that done, so for today and then on Thursday, this is going to be the overview of our lecture. And the only 2 things that we are not going to tackle is 3 and then 4. That's the usage pattern for RNNs and the bidirectional RNN. We don't have ample time. So we are only going to look at 1, 2, and then 5, 6, and then 7. Okay, so the first thing we are going to talk about is modeling sequences. So sequences are bound in NLP, and in language in general, it's full of sequences. Salt Lake City is made up of few words, and these words are composed of what? Characters. And these characters have been arranged in a certain order. If we change the order of arrangement, we will not have Salt Lake City. The meaning will be distracted. So words are sequences of what? Of characters. And characters group together, or when we glue words together, we get what? Sentences. So sentences are a sequence of words, and paragraphs are sequences of what? Sentences. And then from paragraphs, when we compose a lot of paragraphs together, we get a book. When we glue a lot of books together, we compose a lot of books together, we get what? A library. So you realize that sequences are everywhere, not only in language. We could come up with a lot of sequences. But in this case, we are talking about use case in NLP. Yeah, so we've looked at inputs. So from the previous slides that we had, we looked at cases where our inputs are sequential in nature, in the sense that they are of variable size, right? So inputs are naturally sequences at different levels. So at different level, our inputs that we have could be of variable size. So we could have, say, a 1-to-1. In that case, a 1-to-1 array, where in that case it's just a single input and then a single output. At some different level, we want to our model to depict different forms of setup. So at different levels, our inputs are sequential in nature. And our outputs can also be sequential in nature. And we did look at the case where we had a one-to-many and then many-to-many. And in those cases, we realized that our outputs were sequential in nature. Okay, so now let's I think we've looked at other examples, but let's look at this example where in this case our output is sequential in nature because we are fed in an input that's also sequential in nature. So in this case, we feed in Salt Lake City. So what this application seeks to do is that you build a network, and in the network you give it your text or your sentence, and you want it to target each and everywhere. It will target with the part of speech where it falls or it lies. So in this case, John is a noun, so the network is going to tag John as a noun, leaves as a verb, in as a preposition, salt a noun, lake a noun, and then city was a noun. And in this case, you realize that the output we have here is a sequential output because the task we're doing demands that the output also be sequential in nature. So this is one classic application of a many-to-many, what do you call it? RMM, where you feed in an input of variable size and then it produces an output of variable size. So based on the sentence you feed in your network, the size of the output can vary. Okay, I'll skip this. Okay. So now this is a natural question that comes about. How do we model sequential inputs and outputs? Can we assign probabilities to our sequential inputs and our output as well? Can we say that this sequential input is probable? Or can we also say that our sequential output is probable given our inputs? So we want to be able to assign probabilities to these sequential inputs. And sequential inputs that are not probable have low probabilities, and those that are highly probable have higher probabilities. So more concretely, what we're going to do what we want to look at in our lecture for today is we need a mechanism that allows us to capture sequential dependencies between inputs. So we want to be able to differentiate between I live in Salt Lake City and live I Salt Lake City. Because I live in Salt Lake City, the words or the sequences have got certain dependencies among themselves. And then live I Salt Lake City also have got certain dependencies. So we want to find a way or model a mechanism that will be able to capture these sequential dependencies between inputs and be able to differentiate inputs, one input from the other. And also two, we want to be able to model uncertainties over sequential outputs. Okay. So who has dealt with or seen or knows what a language model is? Can you tell us what?
It's a probability space where certain sequences of words have a certain probability of occurring in the wrong.
Good. Thanks. So, as I said, a language model is a probability distribution over a sequence of words. So what you're actually doing is that you're assigning probability to a sequence of words. And sequences that are highly probable will be given a higher probability, and sequences that are less probable will be given a less probability. So in this case, our use case is that suppose we want to build a language model that captures the probability of sentences. So an example is the probability of I live in Salt Lake City should be higher than the probability of live I Salt Lake City. So in this case, we can write our probability as this. So the probability over a sequence of words. So these are the terms x1 to xn are just the words in our sentences or our text. So the probability over a sentence is equal to the products of the probability, the products of the probability of the item conditioned on all the term that comes after it. So this is how we have defined our language model. Okay, so now let's look at an example. So the sentence here is, it was a bright cold day in April. So we want to compute the probability of this sentence. So what happens here is that we first of all compute the probability of the first word, that is it, and then we multiply it by the probability of was condition on it, and the probability of air condition on it was, and then the probability of bright condition on it was air, and the probability of cold condition on it was a bright, times the probability of day condition on it was a bright cold. So all we need is all these probabilities, and then we multiply them together. So that's how, so based on how we define our language model, if you want to find the probability of this sentence, this is how we are going to go about it. But, okay.
Sorry, does it care about capitalization? So like, the I is capitalized in it. Would that change the probability if it were a lowercase I being at the beginning of the sentence?
Okay, so it's user dependent. If it was me that I was trying to do this, I'll just convert everything to lowercase.
Okay.
And then do that. But that's what I'm saying, it's user dependent. But in most of the NLP tasks I've seen, it's either you convert all of them to lowercase and then you work with it, or you just leave it as it is.
Okay.
And then you just work with it. You just give everything to the model and then the model learns it. But if it were me, I'll just convert them into lowercase. Okay, so all right, so I want to ask this question. So based on the language model that we have, and with what we have here, what are the limitations or the deficiencies? Has anyone observed something? Is it a very good language model?
So as the sentences goes longer and longer, then the probability transition, there are too many such transitions.
Good, good. Anyone? Okay, so one limitation here is sparsity, because we could have certain prefixes that we've not seen before, yet alone assign a non-zero probability to it. And also, the probabilities could explode and we will not have a lot of memory to store all these probabilities. So as the sentence grows, because there are some people who talk a lot, so assigning a probability over a lot of sentences or text could explode and you not have a lot of memory to actually store them. And there's an issue of parameter. The number of parameters also grows with respect to the sequence we have. So yeah, so the number of parameters you have grows with respect to the size of our sequence, and that's not good. So now the question is, can we do better? So we can do better by making a modeling assumption. So we use a first order Markov assumption, which assumes that, so the assumption states that the probability of our item condition on all the term that comes before it is equal to the probability of item condition on the I minus 1 term. So we are only interested in just the I minus 1 term, not all of the thing that comes before it. So this is what happens. We are taking away all those dependencies. We are ignoring them and then concentrating on just the I minus 1 term. And this basically simplifies to that. So now this is the new model we have. This is a new language model we have after taking away all those dependencies. And now let's look at how this language model will fare on this sentence. So it was a bright cold day in April. And you want to compute the probability over this sentence. And the result is, we take the first word, compute the probability of it, multiply it with the probability of worst condition on it, and the probability times the probability of air condition on worst, the probability of bright condition on air, times the probability of cold condition on bright, and so on. So this is how, or what our language model is giving us. But there's a little problem here. There's something weird also happening. They didn't really solve our problem about the number of parameters and sparsity. They didn't really solve it. Okay, first of all, I'm not assuming there's a problem. I'm taking back my words. They didn't really solve the problem. Has it solved the problem of sparsity? You think so?
I think so.
Why?
To some degree, I think. At least to solve the, it will have more examples, I think, here. Than previous one, we depend on more previous words. Yeah, it will have much higher frequency here.
That's good. Who else? Okay, so this model, this new language model, they solve the problem of sparsity because most of the pairs here, we've seen them before. And hence you can be able to assign non-zero probabilities to them. Unlike the other one that it depends on a lot of, what do you call it, terms that came after the word, came before the word, and hence you know, there could be some prefix that we've not seen before. But in this case, we have just pairs. And we may have seen those pairs before, and hence you can assign non-zero parameters. And also the number of parameters also decreases. So assuming we have a sequence of input of say k elements, what is going to be the number of parameters? The number of pairs we can have. K squared. So we're going to have k squared combinations. So we're going to have k squared combinations, and it has significantly reduced or helps solve the problem of what you call it, the number of parameters we are facing for the old model. Okay, so now the question is, can we do better? After making the assumption of the, what do you call it, the first order Markov model, we had the results for that model, but we are still asking ourselves, can we do better? And the question is yes. So what we entirely want to do, so what we are asking ourselves is that, can we assign probabilities over the sequences where we do not explicitly remember, what do you call it, the entire sequence. So we are not interested in basically remembering the entire sequence, but we just want to remember, what do you call it, a summary of the sequences as they appear. So that's what we seek to do. So equivalent is the same as saying that, can you discard the Markov assumption so as to also help prevent our parameters from growing. So the discussion we are having here at this stage is that's what is going to set the ball rolling for us to move on, or for our lecture from now going and on Thursday lecture. So the question is, can we do better? So what we are seeking to do now is, instead of we having to remember the entire sequence as they show up, we are just going to remember a summary of the entire sequence by just representing it with just a vector. So we are going to use a vector to remember or to represent a summary of the entire sequence. Is it clear here? Is it confusing? Very confusing. Okay. So let me take it once again. So now we are asking ourselves, we want to do better. And we are saying that, can we do better by, say, instead of when we are computing our probability over our sequences, what we are doing is that we are remembering the entire sequence that they show up. We have P of 8, and then we find the probability of, when a new word comes, we find the probability of that, and then, so it's like at any state that we are in, we are remembering everything. And that can cause a number of parameters to grow or to blow up. And what we are saying is that we want to do better. So now what we want to do is, instead of remembering the entire sequence, we are only going to remember a summary of it. And that summarization is just going to be what? A fixed vector. So that's what we want to do, and that's where RNN comes in.
What do you mean by summarization? Are you trying to convert this into numerical method, some numerical format, and then?
That's a good question, and you'll be answered after this slide, right? So we are going to be a form of the summarization of the entire sequence of the show.
Hidden states.
Come again.
Some hidden states.
Let's wait. Right. Yeah.
Is this similar to like word embedding?
Why are you saying it's similar?
Well,
Is
is the idea similar to the idea of like word embedding, where you're creating a vector of values to represent a word?
Yeah, so
essentially creating a vector to represent a sequence of words.
yeah, in this case we are not doing so. A word, someone can think of it as a summarization of a word. But in this case, for word embedding, what we are just trying to do is that for a set of words, we are just trying to present them in a space, so that if words are equal, they are equal in the terms of similarities, in terms of length. So you could use Euclidean distance. They are going to group together in space. So in this case, the vector, I don't think I would not think of it as a summary of the bias. It's a representation of the word in space, in some space, right? So in some sense, it's not a summary. In some sense, it's not a summary. It's just a vector that represents that word. Are you clear on that?
Yeah, I think so. It is similar to a word embedding, because I think of a word embedding as similar to what you're saying. Is like it's this representation of a word.
Yes.
In space, right?
Yeah.
Vector space.
Yes. So in this case, we are representing it, but it's a summarized version of it.
Sure.
Yeah. Okay. So now we want to look at. So now we know the motivation why RNN came into the picture, right? Hello.
Yeah.
Okay. Yeah. All right. So now let's look at the abstraction of RNNs. Okay. So RNN was first introduced by Ellman in 1990, and RNNs, in a nutshell, we can think of RNNs as a special family of neural network that were designed to cope with sequential inputs, right? So they provide us with a mechanism of representing sequences of arbitrary length into vectors that encode sequential inputs, right? So they are summarizing. So instead of you having to remember an entire sequence that they show up, we are encoding the entire history into just an arbitrary length or a vector of arbitrary length, right? Okay. And over the past, I think 4 years, or 5 years, deep learning has become a de facto tool that is being used in many NLP tasks. So now when you are using your Gmail and you are typing it's what do you call it? It predicts the next word for you. And in some cases realize that that was the next word you wanted to type. And I think they are being used in a lot of NLP applications. You can name them, right? Okay. So recurrent neural network at a high level is just composed of multiple or many single cells, and this cell is called an RNN cell. So in a nutshell, like if on top of your head, if you don't know anything about RNNs, you could just think of RNN as just a network that is just composed of RNN cells. Just many of them without being repeated, stack by side, right? And this RNN is differentiable compute, meaning that it's a computational graph. So this RNN cell is a differentiable compute. In other words, it means that it's a computational word graph. So it takes an input and produces an output. And what happens in the computational graph? There are some weight multiplication there. You can do backward propagation, right? Okay. So one thing that makes the RNN cell very different is that it allows the ability to compose cells. So it allows us, or it gives us that flexibility to be able to glue these RNN cells together. And also, it does not only take in just a single output, it takes in another output referred to as the recurrent inputs. So together with the original input and the recurrent inputs, the RNN cell produces the recurrent output and then the output. So the RNN cell produces two things from the input and then the recurrent input. It produces the recurrent output and then the output on top here. So the recurrent output is basically a memory. It serves as a memory of the past states for the next states, right? So it's something that the recurrent output is basically a memory, a summarization of our past states, which is then carried on to the next state.
So the recurrent input here is just the last step's recurrent output.
Yes. So yeah. So when a new word comes in, the recurrent output will be the recurrent input for the next state. So to summarize everything that I said, the RNN cell takes in two things. That's the input and then the recurrent input. And together with the input and the recurrent input, we produce recurrent output and then the output on top over there. And the recurrent input is also called the previous cell state. So you can keep that in mind. Because as we progress, I will be mentioning previous cell state. And when I do that, you have to know that I'm talking about the recurrent input. Okay, let's look at an example over here. So from all that I've been saying up until now, I just want you to understand that I've not talked about RNN. Like, we haven't produced a recurrent neural network yet. All that we are talking of is a template or an abstraction a computational graph that is going to be used to produce a recurrent neural network. So the RNN cell is not a recurrent neural, what do you call it, network. It's just a template or an abstraction that is used to produce the recurrent neural inputs. So as new input comes in, they are unrolled.
What's the difference between output and recurrent output?
Yeah, and what's the difference between input and recurrent input?
Okay.
If we have a data that is provided to the network initially, that's our input, right?
Yeah, yes, yes.
Then
So
how can we distinguish between input and recurrent input?
So there-
initially we don't have any recurrent signal, right?
yeah, so initially you don't have any recurrent input. So for the first state, you initialize it. So when nothing has happened, when you are starting to build the RNN, you initialize your recurrent input. We are going to see that shortly. Okay. So now let's look at this sequence. John lives in Salt Lake City. Okay. So here, considering our sequence of inputs, that's our sentence, John lives in Salt Lake City. We take the first word, and then we make a copy of the RNN cell. So as I said, the RNN cell is just a template. So we take our first word, that is John, and then we make a copy of it. And the copy of the RNN cell takes an input and then an initial state. So the initial state, you can initialize it to a zero vector of arbitrary length. So you decide the length of it, right? So the cell state over there takes in John and then the initial state. And then it produces the recurrent outputs and then the output on top. So the next word comes in. Then we also make a copy of the RNN cell. So at the new state, we feed in leaves, and then the recurrent outputs of the previous cell becomes the recurrent input for the next cell, right?
This is a training process.
Come again.
This is a training process. Because when you use it, you don't need to fit in any things.
Yeah, so in this case, I'm just talking about how we build the RNN. You've not got into training yet. So we are just looking at the outward abstraction. When a word comes in, how the unrolling happens, right? And we've done the unrolling up until leaves, right? So when the next word comes in, that's what we also make a copy of the abstraction, that's the computational graph, make a copy of it. And it will also take in the inputs in and then the recurrent output, which was the recurrent input, which was the recurrent output of the previous cell. And together we use those two things to produce our output 3 and then the recurrent output. So that's how, so it goes on and on. It goes on and on. So now, what we have here is a massive RNN that was just built from this abstraction, the RNN cell. So the blue boxes you see on top here, each and every box is an RNN cell. And we have glued them together to produce a massive neural network. So now let's go, for now let me talk about the observation. So one thing you observe here is that, as I said, each and every box is a computational graph. And together, they form a very big computational graph, right? So what can we do? We can do backpropagation, right? Yeah. So everything that we know about neural networks from our previous lectures holds here. We can define a loss function at each and every state. And loss functions are differentiable, right? Yeah. So everything that you know about neural network works over here. What you are seeing here is just a computational graph, which has been built from a single RNN cell. Is everyone okay? Okay, so some people like to present everything that I've said. So everything that I've seen here, some people like to present it as this. So what is happening here is that, so it's a neural network with a loop. So you feed in your inputs. So for your first state of at the initial, when t is equal to 1 or 0, based on how you want to start numbering. So at your initial state, you initialize your initial state. Sorry, I'm using those words interchangeably, but I hope you guys understand. So at your initial state, you initialize your initial state, and then you use these two things to produce your recurrent output and then your output. And then this recurrent output here rolls back and becomes your recurrent input for your next cell, and then the cycle goes on and on until your sequence of words, like your input is done. So if you have, say, a sentence of, say, 5 elements or 5 terms, you will have, say, 5 unrolled RNN cells. So that's how it looks. So this is the unrolled version, which compresses everything that we just saw. Okay, now let's look at the map. So now without pictures, let's try and look at what was happening earlier. Okay, so at our fifth step, the RNN cell takes in an input. So here you call the input X sub t. So at our fifth step, the input to the cells is denoted by S sub t, and that is a vector, and that could be a word embedding, right? That could be a word embedding for our word. And also at every fifth step, we produce the cell states. That's our recurrent input and output. And those are vectors as well. And at every cell state, at every fifth step, we produce the outputs, which are also vectors as well. So those are the three things we have to know. So at each step, you compute the next cell state, which is S sub t, from our recurrent function, which takes in your previous cell states and then your current input. So we need these two elements in order to produce our current cell state, and that current cell state will be used for the next cell state. Is that confusing? Okay. And to compute our output, we use this O function, which depends on your current cell state. So at each step, that's what we'll be doing. We use these two things to compute this from our recurrent function, and then we use that to compute your output. Right? And these functions here, R and O, they could be parameterized. And this can be a neural network whose parameters are to be trained. So they could depend on some weights. And then you allow your network to learn those weights. So you could say initialize them at the first instance or at the first time or state. And then you allow your network to learn those parameters from that point. It could also be that the recurrent function and the function O here are not parameterized. So they more or less look like some identity function. You give it something and then produce something. So it depends, it varies. So for Ellman, when you look at Ellman's paper, what happens is that the output here was an identity function. So S of t is equal to Y of t. So that's a use case where the function is not parameterized. So there's no learning going on. There's no training, right? Yeah. Okay, let's look at an example. So I hope everyone is clear what happens at each step. Sorry. So what happens is that we compute the next cell state S sub t from our recurrent function, which takes on your previous cell states and then your current inputs. And we also compute our output, which depends on your current cell state. Okay, so when our first input comes in, we initialize our state, right? S sub O is our initialized state. And then we use that to produce our next cell state. When input S sub 2 comes in, we use our previous cell state. Then we use that to produce our next cell state. So it's like okay. So who can tell me what is happening at S sub 2? Come here.
So you're using what previously held for next.
Yeah. So someone said recursive?
Recursive.
Okay. Alright. They are all very valid points. So let me just add after it. So it's recursive and something that you are calling this function a lot of time, just that the inputs vary, right? Okay. So at t equal to 2, this vector here is basically a summarized version, or it's just the summary of the input S1 and then S2. So in the future, all that the network will see or will remember is just this vector. So you have summarized S1 and S2 into just a vector. And that was what motivated us to look at with RNN, if you guys remember. Because I said that's what is going to motivate everything that we are going to do. So S2 here is just a single vector that encodes our sequence, X1 and then S2. So in the future, from this time going, everything that the network is going to see about S1 and S2 is going to be encoded in S2. The same way, at t is equal to 3, you just summarize everything about X1, S2, and then X3. And from this point onwards, what the network is going to see about these inputs are this. And then it goes on and on. And so on. So, is everyone clear? All right. I think my battery is out. All right, sorry for the disturbance. I had to charge my laptop. So that's that. Okay. Okay, so now we just look at the abstraction for RNNs. And everything we just saw was just okay.
Quick question. So all the output, like what do we do with the outputs? Because it seems like they were just an artifact of each RNN cell, but they didn't have any use necessarily, like going forward, propagating forward. How do we use those?
Okay, so is it the recurrent output or the output?
No, just the output. The output just looked like an artifact that just.
No, it's not an artifact. So the outputs. So let's look at these slides.
Use for loss, right?
Yes. So there are uses for it based on your application. So based on you, let's look at this slide. The usage. I thought I wasn't have ample time to look at it, but once you ask, let's quickly have a look at it and then we move on to it. So now I've used same situation for it. So in this case, for instance, if we were doing say a sentiment classification, after we fill in our word, we build our fully connected layer from here. So like it becomes so that the vector, the output here is going to be used for the fully connected layer, then we attach our loss to it.
Gotcha. Okay.
So they are not just they are not. So it depends on what you are doing. So you realize that here we are not going to use this and this because we believe that the network is summarizing everything that is in here. So at the test state, whatever vector we have here is a summarized version of everything here, right? So we can we can build a neural network and then attach a loss function to it. And so for a text generation task, you could have this where, for instance, we want to generate text like a story, right? Mm-hmm. So after you train on a corpus of fairy tales, you want to let your network generate a test that also have got the probability distribution of the fairy tale that it has learned, right? So you feed in your first word, it makes a prediction of I, and you use that I to also predict what the next word. And in this case, you attach your loss function on top. So the outputs here are not just artifacts. I thought I wouldn't get ample time for us to look at them. So these are use cases of how the outputs will look like, right? Okay. Okay. So now let's look at the L1 RNN. So the L1 RNN is just a simple version of RNN. It's not really interesting, like people don't use it, but it's just for our case of studies, it allows us to understand what is really happening, right? It's just the simplest version of RNN. Okay, so what we've seen previously is what happens outside. And I want to look at what happens within the RNN cell. So at each step, the RNN produces two things: the next cell state and then the output. So for the simple RNN, we also want to see how to generate the current states using the previous states and the current input. That's what is on top, SRT. And also want to see how to generate the current output using the current state. That's y sub t. For this simple RNN, the assumption they made is that y sub t is equal to s sub t. So your output is equal to your state, your current state. That's what I'm saying, that for the Elman RNN, it assumes an identity function for the O. That's why we just kick away the O, because your current state is equal to your output. There's no multiplication, there's nothing going on. What you have is what you get. Okay, so now we are going to build this RNN from bottom to top. So we have these two inputs. That's your current input and then your previous state. So your current input is a vector of size RD, right? So you could assume, you could say when embedding is of size AVN, right? And then your previous state is also a vector of size RDX. So here, the size of the vector is an hyperparameter. And once you have a hyperparameter in your network, what do? You have to do cross-validation, right? To know that. But one thing about this network is that they are very complex and they take a long time to train. So in theory, we have to do the cross-validation, but in practice, these networks are very complex and take a long time to train. So that's that. So if you have ample time, you could do that cross-validation, right? But some networks really take a long time to train. So assuming a network takes like, say, 5 days to train, and you want to do cross-validation, it could be a pain, but so in theory, that's the right thing to do, right? So, okay. So given our previous states, we have this parameter here. So first of all, our t is equal to 1 or 0. At our first state, we initialize the weight, right? And then we multiply. So this is not an array multiplication, it's a matrix multiplication. So this weight here, or this parameter here is multiplied. It's going to multiply to our previous state, right? And it's also a vector of size RDS, right? And then we have this W sub I parameter. So the parameter here is W sub X, which is going to be used for the multiplication, the matrix multiplication of this. And then W sub I is going to be used to multiply our current inputs. And it's also of size RDS. And then we have our, our bias vector, which is also, so you remember, what they are saying that we have 3 vectors on top, which are all of size RDX. And then we add all of them. Isn't this how computational graphs are built? Yes. So that's what I'm saying, that the RNN cells are themselves computational graphs. So everything you know about neural network holds here. Yes, that in this case, RNNs were just designed to cope with sequential units. And then we have, so we sum all of them, and then what happens is that it becomes an input to a non-linear function. So, and it's true, that's what we do for, the network that you've seen previously. Come again?
The activation.
Yes. An activation function. It could be really your times. And then we get our current cell state, right? Which is also of size RDS. So there's nothing new happening. When you follow the step, you realize that it's what you knew already. But just that in this case, it's of a different format. Okay.
Do you only have one kind of layer like that, or can the computational graph have multiple
Yeah, so they are stacked RNNs. I didn't talk about, but they are stacked RNNs.
Okay.
Yeah, they are stacked RNNs. We don't have ample time, so
Okay.
yeah, we have delved deep into also those stacked RNNs. So they are
Okay.
stacked RNNs as well. And we already said that the output is the same as the state. So after you've done this computation here, what you get on top here is your output. It's not parameters. So this becomes our next cell state, and then this becomes our output. So the RNN, everything we saw here is just what is happening within the RNN cell. For the Elman RNN, the computations that we just did in the computational graph is what happens within the RNN cell. What we saw in the previous slide is what happens outside in terms of the unrolling. Now, within a single RNN cell, those are the computations that happen. But in this case, the assumption was that your output is the same as what your state. But for some models or some, what do you call it, RNNs, the output is going to be parameterized. It's going to have some weight, and your what do you call it? Your network has to learn those weights. So in a pictorial view, this is what is happening. You do your multiplication. First of all, your input comes. Those are your two inputs, your current input, and then your previous cell state. And then you do the multiplication with the weights. That's the parameter. And then you get this. You sum them up. You add it. You sum them up, and then you feed it into your activation function, your really your returns. And then, so this would be your previous cell state. And then, since we assume that your output is the same as your state, the output here is the same as your SRT, which will now becomes your next cell state. Yeah, so I think I'm done for today. So on Thursday, we are going to look at 6, and then we're going to look at 6 and 7. That's the vanishing gradient and the long short memory. That's the LSTM, and then your GRUs. Yeah. Okay, so I'm done for the day.
Thank you.
Okay.